Thank you for watching this video. This summary video introduces our proposed novel method named TediGAN that can produce diverse results for facial image generation and manipulation with text guidance. Given a textual description, text-to-image generation can produce images that are consistent with the text. Given a text and an image, text-guided image manipulation is to modify the relevant attributes only and keeping the unrelated ones unchanged. Our method, for the first time, unifies two different tasks into the same framework and achieves high accessibility, diversity, controllability, and accurateness for facial image generation and manipulation. Due to the network design, our method inherently supports continuous operations, high-resolution generation, and multimodal synthesis for sketches and semantic labels with descriptions. To achieve text-guided image generation and manipulation, the first step is to build a dataset that contains photo-realistic facial images and corresponding descriptions. There are currently two popular text-to-image synthesis datasets, CUB for birds and COCO for natural scenes. To fill the gaps in the text-to-image synthesis dataset for faces, following the format of the two aforementioned popular datasets, we create 10 unique descriptions for each image in the Celeb AHQ. The introduced multimodal Celeb AHQ dataset is a large-scale face image dataset that has 30,000 high-resolution face images, each having a high-quality segmentation mask, sketch, descriptive text, and image with transparent background. The key idea of our framework is to map text, image, and other modalities into the latent space of a pre-trained StyleGAN generator, where the multimodal information can learn matching relationships and make the corresponding alignments between text and image. To do this, we first learn the inversion, that is, training an image encoder to map the real images to the latent space such that all codes produced by the encoder can be recovered at both the pixel level and the semantic level. We then use the hierarchical characteristic of the W space to learn the text-image matching by mapping text into the same joint latent space shared with the visual embedding. The layer-wise representation of StyleGAN learns disentanglement of semantic fragments, attributes or objects. The visual embedding and the linguistic embedding are with the same shape L times C, meaning to have L layers and each with a C-dimensional latent code. The control mechanism can select attribute-specific layers and mixes those layers of the style code by partially replacing corresponding layers of content. To preserve identity in manipulation, we propose an instance-level optimization, involving the trained encoder as a regularization to better reconstruct the pixel values without affecting the semantic property of the inverted code. The inversion module aims at training an image encoder that can map a real face image to the latent space of a fixed StyleGAN model pre-trained on the FFHQ dataset. The reason we invert a trained GAN model instead of training one from scratch is that, in this way, we can go beyond the limitations of a paired text-image dataset. The StyleGAN is trained in an unsupervised setting and covers much higher quality and wider diversity, which makes our method able to produce satisfactory edited results with images in the wild. In order to facilitate subsequent alignment with text attributes, our goal for inversion is not only to reconstruct the input image by pixel values but also to acquire the inverted code that is semantically meaningful and interpretable. The training process of the image encoder can be formulated as the objective functions. Through the learned image encoder, we can map a real image into the W space and obtain a latent code W. W is the projected code of the embedding Z in the input Z latent space using a nonlinear mapping network F, implemented using an 8-layer MLP. The obtained code is guaranteed to align with the semantic domain of the StyleGAN generator and can be further utilized to mine cross-modal similarity between the image-text instance pairs. Once the inversion module is trained, given a real image, we can map it into the W space of StyleGAN. The next problem is how to train a text encoder that learns the associations and alignments between image and text. Instead of training a text encoder in the same way as the image encoder, we propose a Visual-Linguistic Similarity module to project the image and text into a common embedding space, the W space. Given a real image and its descriptions, we encode them into the W space by using the previously trained image encoder and a text encoder. The obtained latent code is the concatenation of L different C-dimensional W vectors, one for each input layer of StyleGAN. The multimodal alignment can be trained with the objective function. This module achieves instance-level alignment, that is to say, learning correspondences between visual and linguistic attributes, by leveraging the disentangleability of StyleGAN. One of the main challenges of face manipulation is the identity preservation. Due to the limited representation capability, learning a perfect reverse mapping with an encoder alone is not easy. To preserve identity, some recent methods incorporate a dedicated face recognition loss to measure the cosine similarity between the output image and its source. Different from their methods, for text-guided image manipulation, we implement an instance-level optimization module to precisely manipulate the desired attributes consistent with the descriptions while faithfully reconstructing the unconcerned ones. We use the inverted latent code Z as the initialization, and the image encoder is included as a regularization to preserve the latent code within the semantic domain of the generator. The objective function for optimization is summarized as follows. The two different tasks, that is, text-to-image generation and text-guide image manipulation, are unified into one framework by our proposed control mechanism. Our mechanism is based on the style mixing of StyleGAN. The layer-wise representation of StyleGAN learns disentanglement of semantic fragments, attributes or objects. In general, ICE layer of the latent code represents different attributes and is fed into the ICE layer of the generator. Changing the value of a certain layer would change the corresponding attributes of the image. As shown, given two codes with the same size WC, style code with shape L times C denoting content code and style code, this control mechanism selects attribute-specific layers and mixes those layers of the style code by partially replacing corresponding layers of the content. For text-to-image generation, the produced images should be consistent with the textual description, thus the content code should be the linguistic code, and randomly sampled latent code with the same size acts as style code to provide diversity. For text-guided image manipulation, the content code is the visual embedding while the style code is the linguistic embedding. The layers for mixing should be relevant to the text, for the purpose of modifying the relevant attributes only and keeping the unrelated ones unchanged. To produce the diverse results, all we need to do is to keep the layers related to the text unchanged and replace the others with the randomly sampled latent code. WS and the content code WC could be sketch, label, image, and noise, which makes our TediGAN feasible for image synthesis from multimodal inputs. Due to the control mechanism, our method inherently supports image synthesis from multimodal inputs such as sketches and semantic labels with descriptions. For example, if we want to generate images from other modality with text guidance, take the sketch as an example, we can train an additional sketch image encoder in the same way as training the real image encoder and leave the other parts unchanged. Our method is also able to generate 1024 x 1024 high-quality images. High-resolution images contain lots of facial details and cannot be obtained by simply upsampling from the lower resolutions, making the stochastic variations especially important as they improve the visual perception without affecting the main structures and attributes of the synthesized image. The previous methods produce results that look like a simple combination of visual attributes from different image scales. Some of the attributes contained in the text do not appear in the generated image, and the generated image looks like featureless paint and lacks details. This featureless painterly look would be significantly obvious and irredeemable when generating higher resolution images using the current methods. Our method can produce diverse and high-quality images with an unprecedented resolution at 1024. In general, layers in the generator at lower resolutions control high-level styles such as eyeglasses and head pose, layers in the middle control hairstyle and facial expression, while the final layers control color schemes and fine-grained details. We conduct a layer-wise analysis on the pre-trained StyleGAN we used in most experiments, which is to generate images of 256 x 256 and has 14 layers of the intermediate vector. Based on the empirical observations, we list the attributes represented by different layers of a 14-layer StyleGAN in the table. The layers from 11 to 14 represent micro-features or fine structures, such as stubble, freckles, or skin pores, which can be regarded as the stochastic variation. These stochastic variation are especially important for high-resolution images as they produce lots of facial details and improve the visual perception without affecting the main structures and attributes of the synthesized image. We evaluate our proposed method on text and image partitions, comparing with state-of-the-art approaches ATN-GAN, Control-GAN, DM-GAN, and DF-GAN for image generation, and comparing with MANI-GAN for image manipulation using natural language descriptions. All methods are retrained with the default settings on the proposed multimodal Celeb AHQ dataset. We also illustrate the comparison of sketch to image and label to image generation. These experimental results demonstrate the superiority of our method, in terms of the effectiveness of image synthesis, the capability of generating high-quality results, and the extendability for multimodal inputs. Thank you.